Hello students, in this last video on day 6, we're going to talk about two topics. One is how to calculate some of the more complex probability situations, as well as review the tree model. And you might have seen that from geometry in the past, but we're going to use it fairly heavily. Okay, let's get started. Okay, so we have an example. Rachel has been given a box of chocolate as a gift, and there are 12 pieces in that box. 4 of them are vanilla cream, 4 of them are hazelnut, and 4 of them are cherry. And obviously, you can't tell what's inside chocolate, they all look the same. And she kindly offers her friend May to pick 2 pieces out of that box. And May really likes vanilla. And the question is, what is the probability that May end up choosing to vanilla cream flavor? Okay, let's review again the definition of probability. So the probability of getting a desired outcome is going to be equal to the desired outcome divided by the total of possible outcome or outcomes. Okay? So let's apply this to our particular situation. So in this case, the desired outcome is getting both vanilla. And the desired outcome would be the number of ways that we can get 2 vanilla chocolates. And the total possible outcome would be the total number of ways to get 2 pieces of chocolate. Okay, so we're going to use the knowledge that we've learned from some of the other videos regarding combinations and permutations, and let's count how many ways that we can get 2 pieces of vanilla chocolate. Well, recall from our earlier video, if we have 4 pieces of vanilla cream altogether, and I want to end up with having 2 pieces of it, how many different ways can I get it? Well, that is the typical combination situation, right? I have 4 vanilla altogether, and all I need is 2. How many ways are there? And this is the combination notation of 4 choosing 2. And similarly, if I just want to get 2 pieces of chocolate, any kind, out of a box of 12, that it would be the case of 12 choosing 2. So therefore, the probability of having both pieces being vanilla would be in the numerator 4 choose 2, and then in the denominator 12 choose 2. And you remember how the combination formula works. So 4 choose 2 means it's 4 times 3 divided by 2 factorial, and then 12 choose 2 would be 12 times 11 divided by 2 factorial. And we notice that we have 2 factorial in the denominator of both fractions, so this can be cancelled out, and this is reduced to 4 times 3 divided by 12 times 11, and these cancel out. Final answer is 1 over 11. So the chance that May, in randomly picking 2 pieces and end up having both of them being vanilla, is 1 out of 11. Okay, so this is one way of calculating probability. Let's look at another way. Same example. I'm going to show you how to use a tree structure to map out the events in this case. So because May is picking 2 pieces of chocolate separately, therefore we can represent it as 2 events. And here's how you draw up a tree structure. So you always start with a node represented by black dot, okay, and then you kind of proceed to the right. At least that's the convention I'm used to. So you start drawing a tree depending on what the outcome is going to be from event number 1. So event number 1 would be chocolate number 1. Okay? So May has a chance of picking either a vanilla, a hazelnut, or a cherry, right? So from that original node, think of that as kind of a start of an experiment, okay? It can go one of 3 ways, right? It can go to V, H, or C. Now, after she chooses the first one, then she's going to choose chocolate number 2, and I'm going to represent that as my second event, okay? Because of the limited space, I'm going to draw a little bit weirdly. If you have a large piece of paper, then you can just expand it. So after the first choice, she's going to choose either also a vanilla, hazelnut, or a cherry. Okay, so I'm going to represent it like this. Okay, and similarly, if the first choice she picked was a hazelnut, then she can also end up with a V, a H, or C in her second choice, right? And similarly, if her first choice ends up to be a cherry, then she can also choose a V and an H or C in the second choice. So I'm going to represent another 3 branches here. And on each of the branch, I'm going to label the probability of her choosing that particular flavor. So let's go back to event number 1. So at the beginning, there are 12 pieces of chocolate. 4 of them are vanilla. So the chance that she can get a vanilla would be 4 out of 12. I'm just going to write 4 out of 12 that way. I know I can reduce it, but I'll leave it like that for now. And similarly, hazelnut, same situation, is 4 out of 12. And then cherry, also 4 out of 12. Now, the second situation is going to require some adjustment. Why? Because if she gets the first piece being vanilla, now how many pieces of vanilla are left? There are only 3, right? And of those 3, how many chocolate are left in total? 11, because 1 piece had been taken away. So the chance that she would choose a vanilla in the second event is going to be 3. Let me use a different color. 3 out of 11. What about hazelnut? Well, since she took away a vanilla, so the number of hazelnut is still 4, but in terms of the total number of chocolates is still 11. So the chance of choosing a hazelnut would be 4 out of 11. And similarly for cherry, there's still 4 cherries left, so therefore it's going to be 4 out of 11 as well. Now let's go to the next scenario if she chooses hazelnut in the first event. Well, if you choose a hazelnut, that means there's still 4 vanilla left, but now there are only 11 pieces of chocolate. So the chance of choosing a vanilla would be 4 out of 11. And for hazelnut, because 1 hazelnut had been taken away, so there are only 3 hazelnut left out of 11 pieces of chocolate. And for cherry, because there's still 4 pieces of cherry left, so it's 4 out of 11. And similarly, in the case of her choosing a cherry in the first event, the chance of choosing vanilla is going to be 4 over 11. Choosing a hazelnut, also 4 over 11. And then choosing a cherry would be 3 over 11 for the same reason that I mentioned earlier. And now we're ready to draw our sample space. A sample space would be all the possible outcomes from this experiment. And this experiment, again, is comprised of 2 events, picking chocolate number 1 and picking chocolate number 2. So the sample space is probably easiest to list it in terms of a list that's comprised of the first chocolate flavor and the second chocolate flavor. So I'm going to have VV, I'm going to have VH, I'm going to have VC, then I'm going to have HV, HH, HC, and I'm going to have CV, CH, and CC. And now I can calculate the probability associated with each outcome. Okay? And the way you calculate it is simply by multiplying the probability of all the branches that eventually lead you to that final outcome. Okay, so let me use blue for probability. So for VV, it's going to be a multiplication of 4 over 12 times 3 over 11. For VH, it's going to be 4 over 12 times 4 over 11. For VC, it's going to be 4 over 12 times 4 over 11. And I've written out the rest like so. Okay, so what about the actual probability of interest? So remember, what we want to find is the probability of both pieces being vanilla. Well, which sample or which outcome in the sample space gives me 2 vanillas? 1. Is there anything else? That's it. That's the only outcome that will satisfy my criteria. Okay, so in that case, it's simply that probability. So it's 4 over 12 times 3 over 11. And you notice 4 times 3 is 12, so that cancels out just 1 over 11. And it's the same answer as what we calculated using the method of combinations. All right, another example. Let's say there's a basketball game happening between Fremont High School and Homestead High School. And it's the best series out of 3. So whoever wins the first 2 games would win the series. Okay, a couple more facts. Fremont High School is clearly the favorite. Going into the series is favored with the 2-to-1 margin. And also, once the series gets going, for subsequent games, whoever wins the previous game would have a high chance of winning that game. Which kind of makes sense, you know, you have the momentum, you're playing with more confidence. So let's say instead of 50-50, it's going to be 60-40. Okay? So let's see if we can map out this series of 3 games using probability. And to answer the question, what is the probability of Fremont winning the series? So let's start with game number 1. Okay, so again, we're going to start here. Okay, and it can go either way, right? Fremont may win the first game, or Homestead may win the first game. And remember, because Fremont is the favorite going into the series, so for the first game, it's heavily favored towards Fremont. So let's assume this has a 0.7 chance of winning, and Homestead has a 0.3 chance of winning. Okay, not quite 2-to-1, but for simplicity of calculations, let's just use 0.7 and 0.3. Okay, now after the first game, if Fremont wins, then Fremont is going to have a high chance of winning the second game, right? So, because of the momentum, right? Since Fremont won the first game, it's going to have a 0.6% chance of winning the second game, which means Homestead is going to have a 0.4% chance of winning the second game. Conversely, if Homestead won the first game, then Fremont's going to have a tougher time winning the second game, so it's got a 0.4 chance of winning second game, and Homestead is going to have a 0.6% 0.6 chance or 60% chance of winning the second game. All right, well, let's see what happens at game 3. Well, if Fremont wins the first and the second game, then game 3 simply don't even need to be played. Fremont won the series already, so let's just go right here. We'll just leave it like that. What about if Fremont won the first one, Homestead won the second one, then obviously the game 3 will be played, so you could have Fremont winning or Homestead winning in this case. And again, because Homestead won the second game, so Fremont's going to have a 0.4 chance of winning the third one, and Homestead is going to have 0.6 chance of winning the second one. Sorry, of winning the third one. Okay, let's go down here. Again, I have Fremont and Homestead. Okay, because Fremont won the second game, it's going to have a 0.6 chance of winning the third one. Homestead is going to have a 0.4 chance of winning the third one. And then the last one, because Homestead won both games, so it's just going to stop. The series would stop. They won the series by then. Okay, and now let's do the outcomes. Okay, so listing down all the outcomes in the sample space. So the first one is going to be FF, Fremont, Fremont. The second possible outcome is going to be FHF. And the third one is going to be FHH, each letter signifying which team had won. Okay, the next one is going to be HFF. The next one is going to be HFH. The last one, we don't want to see that, but it's a possibility, Homestead, Homestead. And the way we calculate the probability for each outcome is by multiplying the probability numbers in each of those branches. Okay? So in this case, the first one is 0.7 times 0.6. The next one is going to be 0.7 times 0.4 times 0.4. And the next one is going to be 0.7 times 0.4 times 0.6. And I've filled out the rest as well as calculated the actual probability value by multiplying those numbers together. Okay, so remember we want to find out what is the chance of Fremont winning, right? So in the sample space, let's take off which ones represents Fremont winning the series. Well, clearly this is a win, Fremont, Fremont. This one's also a win, Fremont won 2 out of 3. Not the third one, but this one. Fremont coming from behind, won 2 games in a row, and nowhere else. So the final probability of Fremont winning the series of FHS win series in this case would be summing up all the outcomes probability, okay, that represents our desirable outcome. So our desirable outcome is going to be probability of FF plus the probability of FHF plus the probability of HFF. Okay, and that's going to be equal to 0.42 plus 0.112 plus 0.072, which is equal to 0.604. So roughly 60% chance. So Fremont has a 60% chance of winning the series.